Greetings. Let's go over the topic for 15.1, which introduces the topic for periodic motion with relation to energy. So we are going to define this topic so that we can get a general understanding of periodic motion under this topic and what we are going to be dealing with. Basically, it introduces the vocabulary that we are going to be using during the calculations for this topic. So periodic motion is the motion which repeats itself at regular time intervals. Okay, this is the most important definition for periodic motion. Okay, the motion that repeats itself at regular time intervals. Okay, so for example, you can talk about the textbook mentions too much the motion of a spring, but of course there's a lot of examples like the Earth orbiting the Sun. That is a periodic motion. Okay, so it keeps on repeating itself, and we also get introduced to what is called the simple harmonic motion under this topic. Okay, we get introduced to what is called a simple harmonic motion. So simple harmonic motion is a type of oscillation. Okay, we're going to dig more deeper into this topic in the coming subtopics. Okay, so what is really a simple harmonic motion? A simple harmonic motion is the type of oscillation that has a restoring force. Okay, it's like a spring. You pull it, it goes back to its original position. Okay, it has a restoring force that always tries to bring the system back to equilibrium. Okay, so also, for example, a pendulum is an example of a simple harmonic motion. We are going to dig deeper into this topic. Okay, let's go ahead and discuss energy in periodic motion, and we will take a spring for an example. Okay, so consider a spring attached to a wall like this, and then with a mass with a block of mass over here. Okay, so what is happening is that suppose that this spring is compressed like this. So when the spring is compressed, it is not moving. Okay, when the spring is fully compressed, so to say, it is not moving. So when something is not moving, its kinetic energy is zero. Okay, its kinetic energy is equal to zero. But how about potential energy? Potential energy will be maximum when the spring is fully compressed. Okay, potential energy will be at its maximum when the spring is fully compressed. Okay, so in some of the questions that are you are yet to come across, they will ask you to draw an energy diagram. Suppose they say draw an energy diagram of a fully compressed spring. You have to just draw up some bars, draw a bar for your kinetic energy and leave it empty, and then you draw a bar for your potential energy and just share it, show the potential energy is actually full. Okay, so I won't share all of it, but this is how you can draw your energy diagram. Okay, and then suppose that here our spring was compressed. Suppose that now we release the spring. Suppose that now we release the spring and it goes back to the center. So on its way to the center, what is going to happen is that it is going to reach an equilibrium position. It is going to reach an equilibrium position, and at equilibrium, um, kinetic energy is equal to the potential energy. Okay, at equilibrium, the kinetic energy is equal to the potential energy. So this is one of the important things that we have to know. So remember, when the spring is released, it will be oscillating back and forth, okay, which is why we call it periodic motion. But when it reaches its center, kinetic energy equals the potential energy. Okay, but suppose now that the spring is fully stretched instead. Okay, when the spring is now fully stretched, what is going to happen to the relationship between the kinetic energy and the potential energy? Okay, now our spring is fully stretched. Remember that this happens within a smaller time interval because this is periodic motion. It keeps on oscillating within a small time interval. Okay, so the spring is now in full kinetic energy. Okay, there is now a maximum kinetic energy, and our potential energy will eventually go to zero as the spring is fully stretched. Okay, the spring is in kinetic energy. Okay, so that is basically the important concept about 15.1 in the Eric Mazar textbook. You have to understand the differences between the positions at which the spring is stretched and be able to draw these energy diagrams. Okay, and then the other thing that you have to pick up with regards to this oscillation, we have to know, I've already talked about the equilibrium. I've already talked about the equilibrium position. I've already talked about the equilibrium position, okay? So in which I said that kinetic energy equals potential energy, and another important thing is that the net force equals zero. So this is gonna be one of the important thing to use when we are dealing with calculations for this topic, okay? And Again, when it is fully stretched, you have to know that the distance from its initial position to its final position is your amplitude. Okay, when it is fully stretched, the distance represents the amplitude of your spring. Okay, distance equals the amplitude. That is one of the key points, and then you have to know about the period. Okay, you have to know about the period of your spring. So basically the period is the time for one full cycle. Okay, in this case you already know what period means, but in this case it means the time for one full cycle, okay, of your spring. If it goes back and forth, that's your one period. And then you have to know again about the frequency. What would frequency mean in this particular case? Okay, so frequency will basically represent cycles per second. Okay, still given by the same formula that you know, which is 1 over period. Okay, still given by the same formula, 1 over period. But we are going to look more deeper into this concept. This was just an introduction to periodic motion.